hopefully we'll have enough time to talk about the first 4 things on here. Okay? Finding trig functions of any angle, determining signs of trig functions in each quadrant, and then talking about reference angles and using those reference angles to find certain trig values. Right? Tomorrow, then, we will build the unit circle. So, we've already talked about what an angle in standard position means, right? Standard position just means that the starting side of the angle is the positive x-axis, and then the terminal side lies somewhere after we rotate that initial side counterclockwise. Okay, so today we're going to kind of focus on some point on that terminal side and how to find the trig functions of that angle. These relationships here, okay, are just another way to define trig functions. We've already talked about definitions for our trig functions a little bit. That sine is the opposite over the hypotenuse of a right triangle. The cosine is the adjacent side over the hypotenuse. Okay, but now we're going to start to define them using a point on the terminal side of an angle. Okay, so we're saying that that point we're just defining as having an x and a y coordinate. And then r is the distance from the origin to that point, right? The square root of x squared plus y squared. That's just the Pythagorean theorem solving for the hypotenuse of that right triangle. So they're just calling it r in this case. So sine is whatever that y coordinate of the point on the terminal side is over that distance from the origin to that point, which again is essentially the hypotenuse of the right triangle. Cosine is the x value of that point over r, or the hypotenuse. Tangent is the y value over the x value. And then cosecant, secant, and cotangent are just the reciprocals of these. So we're going to look at how this is basically the same thing as what we've been talking about. This is still going to be the opposite side over the hypotenuse of a right triangle. Okay, we're just going to define it using a point on that terminal side. Just a second to finish copying those down. All right, so let's suppose we have this angle theta whose terminal side has the point -1,3 on it. Okay, so from those definitions that we just talked about, we want to find the exact values of the 6 trigonometric functions of theta. Okay, so we said first, to use most of these, we have to talk about r. And we said that r is just the square root of x squared plus y squared. Okay, well, that comes from the Pythagorean theorem. Right? Essentially what we're doing is creating a right triangle here and saying, well, this side has a length of 3 because that's the y coordinate. This side has a length of -1. That's the x coordinate. And then r, we're saying, is the hypotenuse of this right triangle. Okay? So I mean, you can memorize this x squared plus, or the square root of x squared plus y squared, but all we're doing is using the Pythagorean theorem to find the length of the hypotenuse. Okay. So this is just going to be the square root of negative 1 squared plus 3 squared, which that'll be 1 plus 9 is the square root of 10. Okay, so all we're saying is we've got a right triangle here with these 3 dimensions. Give me all 6 trig functions. All right, now, the trig functions of this angle is actually going to be the exact same as just thinking about this is theta in our right triangle here. And we'll talk about why that is in a second with reference angles. Okay, but this is really all we're doing. So you can memorize that sine is y over r and cosine is x over r, but all we're really doing is constructing this right triangle. Okay, you don't have to memorize all 6 of those things. All you have to know is SOHCAHTOA, basically. Okay. So the sine of this angle, opposite over hypotenuse, 3 over the square root of 10. Okay, and this is y over r, if we want to think about the last slide. We do want to rationalize if we ever have a square root in the denominator. So to do that, we're going to multiply top and bottom by the square root of 10. We'll end up with 3 square root of 10 over 10. Cosine then, adjacent over hypotenuse, will be negative 1 over the square root of 10. Okay, so we do have to make sure that we're keeping our signs straight. We do have to think about the length of this side of the right triangle is negative 1. Obviously, we can't have negative lengths, but since we're in the second quadrant, we say that side is negative 1. So again, we'd have to rationalize, multiply top and bottom by the square root of 10. We'll get negative 1 times the square root of 10 over 10. That tangent, opposite over adjacent, is going to be 3 over negative 1, which would just be negative 3. Then our 3 other trig functions are just reciprocals. So this will be, cosecant will be square root of 10 over 3. Secant will be 10 over, or the square root of 10 over negative 1, which would just be negative square root of 10. And then cotangents, negative 1/3. Questions on something like that? All right, so let's.
No, that's
Actually, we're going to save this part for tomorrow because this is part of building the unit circle. So we will do that tomorrow. And today we talked about coterminal angles. Okay, we've already talked about coterminal angles a little bit. Coterminal angles are just angles that end in the same spot. Okay? Angles that have the same terminal side. So the important thing for this purpose is that coterminal angles have the exact same trig values, okay? The exact same 6 trigonometric functions. So if we are, if we have an angle right here, this is my angle theta, well, a coterminal angle could be an angle that goes around a whole another time, another 360 degrees, or another 720 degrees, right? Just going around multiple times. So that's where this last bullet point comes from. And we talked about this a little bit already. That if we add any multiple of 360 onto an angle, we'll end in the same spot, or if we're talking about radians, any multiple of 2 pi. Now, one important thing to remember is that n could be a negative value. right? We could say, I'm going to subtract 360 degrees from the angle. We'll end up in the same spot. Or subtract 720 degrees, and we'll end up in the same spot. Right? And we'll talk about the signs of the trig functions here in a second. Okay, which ones are positive and which ones are negative in which quadrant. Okay, so again, we just mentioned this, that no matter where that coterminal angle is, if we're adding 360 or adding 2 pi onto an angle, the trig functions are going to be the same. Okay. So let's practice something like this. Okay, find the exact values for the following. Okay, sine of 2,580 and cosine of 17 pi over 4. Okay. Now remember, when it says exact, you can't just type that into a calculator and give you the decimal. Exact means if there is a root on the root, right, like the square root of 3 over 2 or something like that. So to find this, okay, the sine of 2,560, well, what we want to do is start subtracting 360 degrees until we get to an angle that we recognize. Basically an angle that's in between 0 and 360. Okay? So if we start subtracting 360, what do we get? Okay, what we want to subtract 360 until we get to something in between 0 and 360. So start doing that. Start subtracting 360 until we get to something in between. Say what? 60? So the sine of 2,580 degrees is going to be the exact same as the sine of 60 degrees. Okay? Now, we talked about special right triangles a little bit already. Okay, so if we have our, draw it this way. We have our 60-degree special right triangle. This is 60, 30. We said that the side opposite 30 we could call x. Hypotenuse would be double that. And then this side would be x times the square root of 3. Okay, so the sine of 60 degrees, opposite over hypotenuse. Right, so if we include the x's, we would have x times the square root of 3 over 2 times x, right, in our generic 30, 60, 90, but the x's would cancel, and we would just have the square root of 3 over 2. And as we build the unit circle, those will be angles that we'll memorize. Okay, we will just know that the sine of 60 is the square root of 3 over 2. So once we figure out that this angle is just equal to the sine of 60, we should just know sine of 60 is the square root of 3 over 2. But we haven't built the unit circle yet, so we can use our special right triangle for that. Okay with that one? So it's the same idea if we have radians. Okay, we just want to start subtracting 2 pi. Now the practical way to do that would just be to take 17/4 and start subtracting 2 until we get to a value that's in between 0 and 2. Okay, so if we start doing that, just take 17/4, start subtracting 2 until you get to something in between 0 and 2. What do we get? What do we get? Plus. think we get 1/4. Right? If we take 17/4 and start subtracting 2 until we get a number in between 0 and 2, I think we get 1/4 as that value, because I can subtract 2 4 times from this. Right? No. Yeah. No, only twice. I think we should get 1/4 as the value that's left over. Right? So 1/4 pi would be the same as pi over 4. Cosine of pi over 4. If we think about in terms of degrees, because we haven't really talked too much about radians yet, pi over 4, if we convert that, that would be the same as 45 degrees. So we can use our special right triangles. We know that in a 45, 45, 90, both legs are the same. The hypotenuse is that leg times the square root of 2. So if I take the cosine of 45, that's going to be adjacent over hypotenuse. So that would be x over x times the square root of 2. The x's would cancel. We have 1 over the square root of 2. We would need to rationalize though. So square root of 2 over square root of 2. We get cosine of 45. Cosine of pi over 4 is the square root of 2 over 2. Okay, so we're using the special right triangles that we talked about in the last section here. But the idea is to find trig functions of these huge angles. We want to make them equal to something in between 0 and 360 or in between 0 and 2 pi, so that we recognize that angle. Okay. Questions?